In this ProteusDS training session, we're going to go through dynamic analysis of an oceanographic mooring with ProteusDS Oceanographic. What we're going to cover is a review of the mooring design process and of the static load check, and then how to set up a dynamic load check, particularly using a static load check result. We're going to look at adjusting the design and some remarks on sensitivity studies. A review of the design process we've talked about in other training sessions. Typically we start off with a detailed design and get a sense of the static weight and buoyancy effects on the mooring. We can use this, start this step in ProteusDS Oceanographic Designer. Then we go to the steady load check. That's where we're checking the effect on the mooring in steady loads from ocean currents, sometimes winds as well. That may lead us back to the detailed design phase where we change out components and adjust the mooring design accordingly. After the static load cases are done, we then go into evaluate dynamic loads. And oftentimes we're feeding information from the static load into the dynamic loads, of course, and then that again may lead us to going back to the detailed design phase and adjusting the mooring design. So steady loads and dynamic loads are both evaluated in ProteusDS Simulation Toolbox, and post-processing is often done with the report tool and PostPDS. So again, the initial phase in detailed design, we're typically only considering the layout of the mooring and then the effects of static weight and buoyancy only. The second phase, we look at steady loads, static but steady loads from ocean currents most of the time. That's when we see things like deflection of the mooring from a steady current. And the final stage is that dynamic check when we're looking at the effects of ocean waves, possibly also from winds as well. And just again, a reminder that the software workflow is one way, meaning that when you set up a mooring design in Oceanographic Designer, when you're doing your detailed design, it automatically generates the project files for Proteus Simulation Toolbox, which you can then run static and dynamic load cases, and then you're post-processing the results. But that information doesn't flow backwards. If you want to change the design and use stronger materials or use different float sizes, you go back to Oceanographic Designer, make the changes, and go through the process again. Okay, so a reminder how to do a steady load check. Well, when you're in Designer, remember you can adjust the custom current profile that's associated with the mooring file using the environment button here and change the current at different depth points. When it comes time to run the static analysis, use the Analyze button and then pick Static to automatically create the ProteusDS Simulation Toolbox input files. Once we're in Proteus Simulation Toolbox, you can hit the Run button. It should be all ready to go. You can hit the Run button and it'll do some computation in the background to check the mooring deflection and loads. We post-process the results using the Report tool and PostPDS to take a look at it and see the numbers that you get out of it. So this is what you might see, for example, for the full ocean depth softs mooring in PostPDS. It's quite a big mooring in a steady current. And yeah, I just want to reiterate the design spiral you may find yourself going through, starting with the detailed design, static loads in currents, and then dynamic loads in waves. Okay, so I want to get into an example and talk a bit more about the details of a dynamic load check. So what we're going to do is from the sample cases we've got, we can use any one of these really, but we just picked the Del Mar wire walker. I've already got it opened up here in Designer. You can see there's a relatively small current that's set up for it. Oftentimes we want to use the static profile of the mooring to start a dynamic load case. So we'll go Analyze, Static, and I'm going to go Wire Walker, Static. Let's open the files here, so we'll just let that run. Once we've got the static mooring profile, we can use the end state of that calculation process as the starting point for the dynamic load case. And what we're going to use is this export button in Proteus Simulation Toolbox to create a new project with that starting point. So we'll just take a really quick peek at this in post-PDS. Remember, this is only the statics. We're in orthographic already, that's great. Engineering view, looking for the east. So the diagonal line is just a initial starting condition. That's a zero current condition, and then here's the mooring in the relatively weak shear current profile. All right, okay, looks good. So we'll go export, and we're going to call this dynamic, and open the project. We can close this now, we don't need that anymore. Okay, so we need to do a couple things first. Convert the D object. Quasi-static cable is used for our static calculations. The only thing you can convert it to is cable for dynamics. And that's the D object type. We're going to change mooring. That's the one that we've got there. So we do that. It uses the same input files. It's just making taking advantage of the dynamics that cable can calculate. We need to pick a simulation length. We'll talk more on this in a moment. But just to get started, I'm just going to do 200 seconds. And we'll need to have a bit more fine-grained file output rate. So we'll change that to 0.1. We need the current effects on, and we're just going to turn on some waves. I'm going to pick out of this a John swap wave state. So we'll type in 8 here, right-click, resolve follower properties, wave height 5, wave segments. We'll talk about this as well with the repeating wave surface. I think we're ready to go. Okay, while that's running in the background, we'll check in on this later. Let's go back to the presentation here. So we've exported, we've converted the object, we set the simulation time, and we've added some waves. It's most common to use John swap or Pearson-Moskowitz. I want to talk a little bit about C-state realizations. Remember that a wave spectrum is kind of like shorthand for a C-state condition. Really, this is a frequency spectrum, so it's not really giving you the actual time series information about the C that was there. What this means is if you have a spectrum, then there's an infinite number of real C states that may have the same spectrum. The surface time series is compressed into a spectrum, basically. So what this means is, here's 3 examples of 3 different time series of water surface. They all have the same spectrum. They've all got the same significant wave height, but you can see, well, they're not quite the same. And you know, there's peaks, peak wave crest and trough that's pretty big here, and the other ones maybe they have something similar, but they're not exactly the same, and they don't happen at exactly the same time. So when we talk about C-state realizations, we're really looking at more than one realization of the same C state. And why is this important? Well, a mooring may have a different peak load depending on the realization that you're looking at. So it's generally good practice to look at a couple of different realizations, even if it's the same C state. And then what you really want to do is watch the variation of the magnitudes of those peak loads between the realizations. There's maximum and minimum outputs reported in the report tool. This also gives you feedback on if you've run your simulations long enough. You know, how do I pick, you know, the right simulation length? 200 might be a little bit short, but that's one way of checking it. So oftentimes, you know, like 3 realizations might be a good start. If there's too much variation between the peak loads, it means that maybe your simulations are too short. You really need to be looking at longer simulations and just let the dynamics resolve a little bit more and really give you a feel for what's happening in the simulation. If there's too much variation, it may mean there's a lot of snap loading that's happening in your mooring, and the solution is not more and longer simulations. It's, you know, how do you change the mooring compliance? Is there a way to change the design so you're avoiding these slack conditions, which then lead to snap loads and things like that. So remember that some variation is fine and normal. You're never going to get exactly the same, peak loads, but just, they shouldn't be hugely, the peak loads shouldn't be hugely different from each other. And in terms of, the number of segments that make up the spectrum, that's what the wave segments parameter is. So I put in 75 here, but if you put in only one, well, this is the number of sinusoidal wave components that make up the spectrum. If you have only one, then you've got a sinusoidal C state. It's not a good representation of the spectrum. If you have several, to run these in batch load cases, when you've got several folders with either a different number of C-state realizations, or maybe you even want to check different C-state conditions and magnitudes, you can do that really easily using Proteus Queuing Manager. So I've still got this one simulation running, and I've just called it dynamic, but we could make copies of this. Call it seed 2. Everything is exactly the same. Seed 3. Let's open this up. Oh, well, those results will be partially finished, so we're going to get rid of those. This is where the seed number comes in. So everything else is the same, but it's going to use a different seed to set the initial wave phases, randomly set the initial wave phases of all the wave components in this C state. So as long as the number is different, that's the main thing. This is, again, initializing the random number generator. So anything can be different than what's already there. So just keep it a little bit simple. And we'll do the same thing with this one over here. So we're just going to use something with a different seed. So now we're looking at 3 different C-state realizations. When you use Proteus Queuing Manager, this helps you run things in parallel and run through large batches. It'll detect how many cores you have on your computer. So I'm just going to do 1 for now, and then it'll run all these through the queue, which is really great. I just wanted to demonstrate using PQM, so I'm going to stop that for now, and then we'll take a look at our dynamic loads in this one in a moment. Right, when using the report tool and looking at the results, especially when running from a static load case, we're going to check this in a sec. You typically want to truncate the first 10 seconds, really, of any dynamic load case, just to make sure you don't have any artificial transient loads in your tensions that might be influencing the results. So how many realizations should we really check? Well, I said maybe 3 might be a good starting point, but is that what you use all the time? Well, it kind of depends. It depends on how long your simulations are. It depends on your experience and what you're comfortable with. But generally speaking, you're really trying to make sure you're not seeing a lot of variation in the peak loads between the realizations. When we were looking at something like a full ocean depth mooring in extreme storm conditions, we were looking at 500 to 750 second simulations, and that gave us pretty consistent peak loads between different seeds. And at least 3 seeds is a good starting point. And remember, you can always do more. Minimum safety factor 1.67. You really need to make sure your loads are greater than that, than the minimum braking loads. If you want to reduce your uncertainty, you can always run more and longer simulations. These are just some results from a couple of different realizations. So, from one seed, is seeing a peak load of 44 kilonewtons. From another seed, 45 kilonewtons. From another seed, 48 kilonewtons. And, it's just kind of giving you an idea of the variation across the different realizations. And there always should be some variation. Just note the oil and gas industry for mooring systems for like a floating production, storage, and offloading system, which has a very slow yaw natural frequency with peak loadings perhaps on the order of hundreds of seconds. the expectation is to look at something like maybe 15 to 20 realizations for a load case, and much longer, um, and much longer simulations to pick up on those peak loads that happen every 200 seconds, which are significantly larger than the wave-induced loads. So just to give some context, for comparison. And it's always good to do a reality check if you can, and just get a visualization. This is the soft mooring at full ocean depth in a storm condition, to make sure it looks like sensible. So again, just a review of the design process. Starting off in detailed design, so we did a static load check with the wire walker mooring, and now we've exported those results and we're checking a dynamic load. So we've got about a minute done here in the simulation, and I think what we're going to do now is just pause this and let's do a quick peek and see how it's coming along. And we'll go to perspective view. You can see it's getting a little bit slow with that number of wave segments. So I'm going to actually go back to engineering view here. Be aware that oftentimes it'll truncate the number of wave segments just to help with the computational speed. But it's a good idea to look at all of them. Otherwise, it might look like the buoy's not tracking the surface. So you can see the wire walker buoys following the surface really nicely, which is great. It's not getting submerged. And if you want to, you can see what the tensions look like. Some peaks as the waves are passing by. So some interesting results. Generally, it kind of seems kind of realistic, so that's good. So going back to adjusting the design, how do you make sure you have enough mooring compliance? Well, maybe you need to change the float size if you have a midwater float. Of course, you might need to adjust line size and length. And again, you have to do all of this in Designer, and you really want to find ways to get that mooring compliance so your system has some give and take in it when the waves come by. Again, you'll have to flow through the process once you've made changes in Designer, export to Proteus Simulation Toolbox, and run it again and run the report tool. Consider that really small changes likely don't affect simulation results. So if you're changing shackle sizes and in a really big mooring, maybe the results aren't going to change that much, just because a shackle is only a fraction of the total weight. Sensitivity studies. So don't be afraid to make changes and then really explore how these changes make an impact on the response in your design. So buoy form factor for the surface float, larger line size. Can you reduce major components along the line? If you've got a frame, can you use fewer frames or maybe reduce frame mass somehow? Sometimes the larger frames you have, they create a lot of dynamic loading because they're just so heavy, and when they bounce around when there's waves going by. If you've got a range of sea states to check at a particular location and a range of peak periods, it can be tricky to figure out, well, what's the worst case scenario? And it might be a trap to jump to the sea state with the largest significant wave height. Sometimes the worst loadings you get in a mooring is when you have the maximum wave steepness, and that's not always, of course, the same state as the wave with the sea state with the biggest wave. Steepness, of course, is going to be sort of a ratio of the height divided by the wavelength. And that's certainly the case that we found with the soft mooring as well. The biggest wave heights seen in the Southern Ocean from this mooring were on the order of almost 20 meters. But the periods were so long that they just weren't that steep, and they didn't really create a lot of dynamic loading in the mooring. It was more like the significant wave height around 10 meters that which had the biggest steepness and the greatest acceleration on the buoy, and then the resulting mooring with the greatest dynamic loads that caused the problems. Be aware of fatigue loads as well. You really need to check multiple sea states and understand how fatigue life changes with the variation in the load standard deviation. So in review, we looked over the mooring design process and did a review of the static load check, showed how to start a dynamic load case from a static load check. We talked about adjusting the design and working through the workflow, again, starting with designer, doing static check and dynamics as well. And again, just really want to encourage the use of sensitivity studies to explore the design space and understand how the mooring responds to changes in materials and floats and things like that. All right, thanks for watching.